Hello everyone, I'm honored to attend this conference and today I'd like to introduce our work on behalf of my team. Our topic is an attention self-supervised contrastive learning-based three-stage model for handshake feature representation in Q-speech. And the first part is introduction. Q-speech is a communication system for deaf people or hearing-impaired people, in which a speaker uses it to aid a lip reader in phonetic level by clarifying potentially ambiguous mouth movements with hand shape and positions. Feature extraction of multi-modal Q-speech is a key step in Q-speech recognition. Currently, lip and hand position feature extraction has achieved good results. However, there are still some challenges which limit a good hand shape feature extractor. Firstly, the movements of lips and hands are asynchronous in Q-speech, while most of the proposed hand shape annotation methods rely on audio-based segmentation. This causes noisy hand-shape annotation for Q-speech data. Secondly, since the hand shape changes quickly when it moves, for example, the same hand shape with fast-moving variable rotations, occluring, and motion blur, causing different appearance. It's difficult to extract accurate and robust handshake features. Indeed, most previous works ignore the variability and complexity of handshake in Q-speech. Thirdly, the limited Q-speech dataset brings great limitations to the deep learning-based methods of Q-speech handshake feature extraction. As present, the published Q-speech datasets merely include a single-speaker French dataset and a single-speaker British English dataset. And the contributions of our work are mainly divided into the following 3 points. And the next part is our model. To improve the performance of Q-speech handshake feature representation, in this work, we propose a 3-stage handshake feature extraction model. The first module is self-supervised contrastive learning-based handshake feature representation. We perform a random transformation on input images, including cropping, horizontal flipping, color distortions, grid level distortions, and Gaussian blur. Then we get 2 related images at the same instance. And next, ResNet 18 is used as a basic encoder to extract the representation vectors. 2 nonlinear fully connected layers are used to map the feature representation to the space, where contrastive loss can be applied. And after that, a contrastive loss function is applied to calculate the loss of positive pairs. And the second module is manually annotated data-based fine-tuning. We fine-tune the model with 10% data of the training set, which are manually annotated to obtain more accurate handshake features. We directly feed hand ROI to the pre-trained ResNet 18, obtaining the handshake features and feeding them to this module. 2 nonlinear fully connected layers are used as the classification network in this module. Based on the above 2 modules, we can extract accurate spatial handshake features. However, Q-speech hand shape is a video sequence. Thus, contextual information is also important. To learn temporal and sequential information of handshapes, we combine bidirectional long short-term memory and multi-head self-attention networks. Among them, bidirectional long short-term memory models the global information of a sequence to extract features with temporal and contextual information. And self-attention networks learn the internal dependence of the sequence so as to better model the internal structure of the sequence and emphasize the important information. And last, in order to make full use of the features learned from bidirectional long short-term memory and self-attention networks, we use a shortcut connection to add their outputs. The next part is evaluations. This is the dataset we use. The French dataset contains only one person's data, and the British English dataset we build contains five persons' data. The label in the upper right corner shows the number of sentences contained in each dataset. And we use classification accuracy, phone error rate, and phone correction rate as valuation metrics. At first, to verify the influence of noisy data on handshake recognition performance, we compare ResNet 18 directly trained with noisy data with ResNet 18 trained with manually annotated data. ResNet 18 trained with manually annotated data achieves over 30% improvement on both French and British English Q-speech datasets. Then, we compare our model, which only contains stage 1 and stage 2, with ResNet 18 trained with manually annotated data. In both our model and ResNet 18, we use the same amount of manually annotated data. It can be seen from the table that our model performs better because the self-supervised contrastive learning module makes full use of noisy data for feature representation. And finally, we mix French and British English Q-speech datasets for training. And the results show that our model is not affected by multiple speakers. And next, to verify the effectiveness of the extracted handshake features, we qualitatively visualize the feature map of hands in complex scenes. From A to E are transition from handshake 1 to handshake 3, and the images of self-occurring handshake 2, partial hand occurring handshake 6, twist handshake 8, and motion blur handshake 5. It can be seen that although the handshapes are very distorted or fuzzy, our model can still capture the key feature regions and recontrast the handshape. And the recognition results of continuous handshape in each dataset can be seen in this table. Each time the handshape sequence in a sentence is identified, compared with the sorting method, a significant improvement of 16.42% correctness is achieved in the French dataset. And in the British English dataset, our model also achieves high accuracy. And ablation study shows that all modules in our model are important. And compared with the model trained with noise data, our model achieves much higher handshake recognition correctness. Finally, we consider Q-speech phoneme recognition, which uses the lip, hand position, and hand shape as the input, and the output is the phoneme class. The comparison under different models shows that our model achieves the best results on both French and British English datasets. Compared with the sort method, 10.75% and 10.09% improvements are achieved in the two datasets respectively. This verifies that our model can still perform well in multilingual and multi-speaker scenarios and reduce the influence of noise data on Q-speech phoneme recognition. And the last part is conclusion. In this work, we propose an attention self-supervised contrastive learning-based three-stage handshake feature extraction model. And our model solves the problem caused by the noisy annotation in Q-speech handshake feature extraction, and the experimental results show superior performance to the sort methods. But as for future work, we will explore the effective sample pair selection methods for self-supervised contrastive learning in Q-speech video. Okay, that's all of our work, and thank you for your listening.